Okay, good morning, everyone. Today we continue a discussion on linear programming. As we talked in the last week, is the mathematical model that we use for solving prescriptive problems. Last class we talked about some of the language of this domain, like shadow price, binding, and non-binding definitions. Also, we had a problem. Basically, it was an old problem about making a meal plan using hash brown sandwiches, and we just use Excel instead of graphical approach. So, and we have talked that human brains are mostly limited to up to 2 or 3 dimensions. More than that, we just have to use softwares, but we need to know what those concepts means. Like we talk about, I think, surplus, slack, and we said in the Excel both of them are actually the same, but in most of the softwares, surplus is just related how you are far from greater than equal constraint, and slack means how you are far from less than equal constraint. And we talk about shadow price, allowable increase, and reduce cost. Just as another example, let me show you through my board. Stop here. Okay, let's say in our case, this is the optimal point. Can anyone remember what are my binding constraints?
The yellow and red line?
Yes, because they are contributing in the point that is our optimal solution or optimal point. So let me just draw another one. So in here, number 4 and number 3, or black and green lines, are not contributing. So they are not binding. Also, we talk about shadow price. Can you remember what was the definition of shadow price? I just took it today, so no worries. So changing the objective value when you change a constraint or a resource. So here, if you change line 2 or yellow and line 1, I mean, let me just move line 1 or the red one upside. So this would be the new line. And maybe, most likely, this would be my new optimal point. So as you see, the binding constraints has a shadow price, because if you change them, you definitely change the optimal point. Here is either go upside down, so you're changing the final solution. So basically, when we are talking about binding constraint, It just means this is synonymous by saying that their, shadow price should be different 0. And again, there is no mathematics behind of it. We just have some terms that you need to know, because later you look at some reports and you might say, what is shadow price? Okay. What are shadow price of line 4 and 3? What do you think? Could anyone tell me the shadow price of line 4? So if you change line 4, either you change it up or down, does it have any effect on optimal point? There's no effect, right?
No effect.
Yeah. So the shadow price, so the shadow price is 0. So again, there is no mathematics behind of it. We're just saying that for non-binding constraints, is almost synonym of saying that shadow price is equal to 0. Also, if I change line number 3, either up and down, it doesn't have any effect on my optimal point. So here, 3 and 4 are non-binding. Again, non-binding means shadow price 0. Binding constraints are 1 and 2. It might be a little confusing at first, but if you just have some experiences, it's just very straightforward. There's nothing, again, no mathematics behind it, just some definitions. Okay, I think there is a typo here, so let me fix it again. So number 3 and 2. So number, okay, I think 1, 2, 3, okay, never mind. So 1 and 2, my binding. 3 and 4, not binding. I would think I erased it, but no, I didn't. So also look at the optimal point and line number 4. Do you see there's a distance here? So when our optimal point is on the binding constraint, it just means those constraints intersect each other. It's the only way that make a point. Having said that, means that point is on that on the constraint, so the slack should be 0, or I mean surplus anyway. Also, but for the non-binding constraint, we have either surplus or since we are mostly work with Excel, let's just name all of them slack. Not differentiating between slack and surplus. But for line 1 and 2, which are binding constraints, also we don't have any slack or surplus. Any questions? Again, I don't expect you to memorize it. Just remember what was the meaning of binding constraint or shadow price, or what does the definition of slack? What we meant when we said slack or surplus? It just means how you are far from the constraints. We also talk about reduced cost and allowable decrease and increase. I mean, it's very hard to visualize them. It just basically means some of the decision variable are 0. How should we change their coefficient so their final answer shouldn't be 0? So, and also allowable increase and decrease means how far you change the coefficient, but you change to the extent that you change coefficient, but at the end the final solution would be same. So these are through practice, but optimal points, shadow price, binding constraint, slack and surplus, you can kind of visualize them. Okay, so sorry if today I don't speak well. I had a lot of stitches inside my mouth, so it might be a little hard for me to talk today. Okay, so let's go to the next problem. Okay, again, the way that you learn prescriptive analytics is just through more and more types of problems. You should see a lot of examples. So at the end, when you see a newer one, you just, in your mind, you try to find some similarity between what you already experienced, and you will be able to solve them. So there is a lot of mathematics under the hood of these algorithms, but we just want to see how we can use them. We don't care about the math. So, and most likely in the future, if you see such a problems, you need to just formulate them in the way that is acceptable for a software. I mean, like here, for now, we are working with Excel. Having said that, you just need to do a lot of practices. You need to see so many types of problems, which for the next one is just make versus buy decisions. So if you're in the supply chain part of your, company, or if your company depends a lot on the supply chain and it's an important part of your company, most likely you would face such problems. Okay, let's look at one of them from the make versus buy decisions. Let me read. A company titled Worcester Balls produced 3 kinds of footballs: ball 1, ball 2, ball 3. Due to increasing demand, the production at own facility is not enough for this month. This month, a total of 3,000 bags of ball 1, 2,000 bags of ball 2, and 800 bags of ball 3 are required. So this is our demand or order. So you have an order for this month, and you are not able to just make everything in home. So look at the middle table. So as you see, when you make them by yourself, you pay less. So for example, ball 1, if you make in-house, you pay it costs 52, but if you purchase it, you should pay 61. Same for ball 2 and ball 3. Having said that, we have some constraints and some policies. Let's look at them. So based on like internal policy, at least 4,000 bags of football should be produced in-house. These 4,000 either could be just general policy, or maybe you have another production department or accounting department. They might say, if you're producing less than 4,000 bags of footballs, it's not economical to run the manufacturing plant. So some of the policies maybe have other reasons, some are just purely policy. At max, 1,000 bags can be ordered from outside. It could be just general policy, not any economical reason behind it. So HR would tell you that you just have 10,000 hours of labor. We don't have, everything is limited in this planet. So for your company, hours of labor is just 10,000. And you know, for ball one, it costs like 2 hours of manual work. For ball 2, 1 hour, and for bag of ball 3, 3 hours. Also, labor cost for ball 1 is $7, ball 2 $8, and per bag of ball 3 $7. Okay, so having said that, if you just look at this problem, anyway, just let me give you 2 or 3 minutes to read that by yourself and think about it. Then we go to the next steps. Can anyone tell me this is a maximization problem or minimization? Do you think for your objective function, should you maximize something or minimize something? So if you look at the problem, just since we have costs, right? So does it make sense if you maximize your cost? So
you would want to minimize your cost and your labor.
yeah, I mean, labor is associated to the cost, so either of them, yeah, that's right. And at the same time, you want to follow these policies. So this is just a plain English. I mean, is maybe first step we just try to formulate them, and then just convert in a way that Excel can understand. So M1, M2, and M3. Oh, I think I jumped. So M1, M2, and M3 are just decision variables about number of different types of ball that you make in-house. While B1, B2, and B3 is decision variables for number of balls that you buy for each type. And these are the only decision variables. And we also, for each decision variable, we have a coefficient here. Like, let's say you make 2 balls for ball 1, you buy 2 and make 2. I make 3. So if you make 3 of ball 1, you should pay 52 times 3, and if you buy 2 of them, you should pay 61 times 2. And same for other types of balls. Okay. Now, using the coefficient, we can make our objective function. For each type of balls, either you make inside or in-house, or you order them, you have different coefficients, and basically just summarize this table to this equation, minimizing the cost, which is just an amount of decision value multiplied to its cost coefficient. Okay. Now we try to formulate our constants. So first constant, at least 4,000 bags of football should be produced in-house. M1, M2, and M3 at least, so means greater than equal. Also, at most or at max, 1,000 bags should be ordered outside. So we know B are associated to buy or ordering outside, and they summation should be less than equal 1,000. Also, we had demand. We just said demand. We know that demand of ball 1 is 3,000. So you either buy or make. So the summation should be 3,000. Same for ball 2. Either you make M2 or buy, it should be 2,000, and same for ball 3. So if I change it to greater than equal, or maybe greater than equal 2,000. So what does it mean? It means I expect the order should be more than that a little bit. So I try to impose greater than equal equation in case if I'm more demand a little bit, I don't lose the opportunity. But in this problem, the policy is just exactly 3,000, 2,800. Now let's make our labor and budget constraints. So we have coefficient of labor for making. So for ball 1, 2 hours, ball 2, 1 hour, and ball 3, 3 hours. And you see 2, 1, 3 multiply to amount of decision variables. And we know the hours should be less or equal 10,000. You don't have more than that. For budget, we have the cost of making them. So 787 for ball 1, 2, and 3. And based on our policy or maybe our budget, we don't have more than 35,000. So this is our budget constraint. And non-negativity condition, we know that all of them should be at least 0 or more. They could be 0 means, let's say if M1 is 0, means I don't make any M1. So for ball type 1, I should purchase all my demand from somewhere. Any questions? So I give you 1 or 2 minutes to just focus on it, then we go through the Excel solution. Okay, so if you understand how to formulate it, the Excel is nothing just basically typing these formulas into Excel. So let's open Solver, and you should have the solution same as me. We talked about how to formulate it. First of all, for constraint and objective function, we know that we should formulate them in the way that by changing decision variables here on yellow, this blue one, which is my objective function, and this, let me just change to orange. Orange, basically this blue one, which is my objective function, and these orange ones should change based on amount of decision variables. We know for objective function, it just means coefficients of the objective function multiplied to decision variables. And same for constraints. So like this constraint just means 1 times m1 plus b times m1. And we know it here should be equal. So, and we check if they're equal with 3000 or not. So you formulate the constraints based on their coefficient in the constraint times the decision variables. And if you click on each cell, you can see how it formulates. Let me check the last one. The last one is 7 m1, 7 here, m1 here, but m1 is empty. We don't know how much we don't know about this decision variable yet. 8 times m2 means d13 times d4 plus 7 times m3. So is e13, right, times e4. E4. And the remaining are 0, so you don't even type them. So let's go to the solver. So first of all, I just mentioned what is the location of the blue cell, which is my objective function. Then the type of the problem is minimization. And the third part, you should mention where are your decision variables. We know that these are my decision variables. And for each constraint, we know that their value should be in the orange cells. For first one, second, and third one, it should be equality, because based on the problem policy, number of balls should be exactly equal to 2000, 2800 for different types of balls. So these are my equality equations. So I7J7, I7J7, I8J8, and the last one, I9J9. And same for other equations, like this equal, less or equal or more than equal. And the last section, it just, you say all of the variables should be non-negative. So again, the big picture is this Excel solver needs 3 sections, 3 major sections. First, location of your objective function. So in the blue cell, so anytime you want to click a cell, first click inside Excel solver parameters, then go and click here. So I5 has the location of my objective function. Then you should identify decision variables, the yellow ones here. And the last part, you should build your constraints. So the left side, let's look at this equation. First equation, m1 plus m2 plus m3 equal 4,000. So the right side is 4,000, as you can easily see here. The left side, you should build that m1 plus m2 plus m3 formula inside that cell. Let me just click on it. M1, 1 times m. No, not this one. Yeah, is this one. So, not this. Okay, this one, this equation. So let me show it here. So m1 plus m2 plus m3 get to equal 4,000. So inside this orange cell, I made that formula. How? M1 decision variable times 1 plus M2 decision variable times 1 and M3 times 1. Any questions? And same for other ones, like so the orange cell has the formula of left side of the equation. Right side is that 35,000. We just through Excel solver, we just say the left side less or equal right side. This one. And how you just each time you add a new equation by just putting the left and right side less equal or greater, and that's it. So let's just solve it. And okay, it seems we couldn't solve it. So let me see what was the issue. So okay, I suddenly click on the decision variables. So decision variables should be this part. Okay, this is the final answer, objective function. Let's look at the reports. We just have one unbinding constraint for this one, so J12. So as you see, this time, I mean, all of the constraints are basically contributing the final answer, except for constraint number 6 or resource constraint 6. So we just use 9,000 hours of labor, not all. But look at them. This one, the left and right side, 3,000, 2,800, 4,000, 1,000, except for this one. So can anyone tell me the shadow price of the resource constraint number 6? We know that it's not binding. If you remember, when there is a distance from your constraint, that constraint is not binding. So the slack should be 1,000 here. Let's see, yeah. When there is a slack, it just means that constraint is not binding, and a slack 0 means they are binding, as you see. Might have a little confusion what I'm saying you, but these are just, I mean, some language. Whenever you see a slack or said it's not binding, means that constraint is not attending in the final solution. It's the final point. So the final point has intersection of these 4 plus 2. So 6 lines intersect each other and made that optimal point. The allowable increase and decrease are okay. Okay, so problem number 3. So far we have seen 2 types of problem. I mean, how to make a meal plan is could I say it's like a composite problem. The second one, make or buy problem. And the last one is a transportation problem. So we have 3 farms and 3 processing plants. So or groups. So one is Mandor, and it has 21 miles distance to Ocala, 50-mile distance to Orlando, and 40 miles distance to Leesburg. Farmer groups, Ostas had 35 miles to Ocala, 30 miles to Orlando, and 22 miles to Leesburg. And similarly for Kellermont. Kellermont had 55 miles to Ocala, and similar, like 20 to Orlando, 25 to Leesburg. Each group has different supply. I mean, the Mount Dora has 275K, Ostas 400K, and Kellermont 300K. And we have also, we know the capacity of processing plant, 200K for Ocala, 600K Orlando, and Leesburg 225K. Here, our decision variables is just how many load or how much cargo you send on each link. You know, a processing plant, you should you do your best to supply them with from your groups. Also, you know that distance of each connecting line from a group to a processing plant is different. So here, what's your idea? Do you think it's a minimization problem or maximization? Here, instead of cost, we have distance, right? Can anyone guess?
It should be a minimization problem, shouldn't it?
Yeah. So you're sending through different links, and you don't want to travel too much, because traveling more, you should pay more, and you should spend hours. So here's also minimization. You don't want to drive too much. You want to make your driving distance smaller, because like less drive, less cost. So you're trying to minimize the driven minds. It just means it's synonym with you want to reduce the cost. So yes, very good guess. It's a minimization problem. I give you like 5 minutes, no, not 5 minutes, too much, or 2 or 3 minutes to read this problem, think what could be your idea, then to go to the solution. Just spend like 1 or 2 minutes to think about this problem. I think making objective function should be easy, because you know that the decision variable is just how much you send from each supply point to the demand point. So basically here, can you tell me how many decision variables you think we have? We should decide how much cargo or how much load we want to send on each link. So basically for each link, we have a decision variable. It could be 0 even. So, but for each link, we have 1 decision variable. So what is the total number of decision variables? Yeah, I don't see your faces, but okay. So for each link, we have a decision variable, because we want to decide either do we want to use that link or not. We have 3 links for Mandora, 3 for Ostas, and 3 for Kilomat, so 9 decision variables. Maybe at the end, we don't use half of them. It could be half of the decision variable would be 0. But again, they are decision variables. So you might say some of the links are very long, like Mandora to Orlando, but we have some limitations. Maybe at the end, we use that link or not. So at the end, we have 9 links. We might use, or we may or may not use them. So for each link, 1 decision variable, at total 9. We want to minimize it. So x1, 4x1, 5x1, 6, similar to 2, 4, 2, 1, 2, 6. So each of them has a distance. The distance is their coefficient. So we have 9 coefficients. We are trying to minimize the distance. So if I give you another problem, and the problem, instead of distance, you have cost. When you make objective function, instead of distance as a coefficient, you have cost as a coefficient. I just wait 1 minute to if you guys have a question. So as you see, first time you see transportation problem might be challenging, but next time if you see something similar, it's much more easier, believe me. So if I tell you in the homework, instead of distance, I put cost, you just change distance coefficient to the cost coefficients. So look at the first two rows of constants for Ocala, Orlando, and Leesburg. I said less or equal. So first of all, x1 for x2 for x3 4 are these three links. It just means from 1 to 4, 1 to 5, 1 to 6. Look, 1 to 4, 2. Oh, I think, okay, let's look at this one first. 1 to 4, 1 to 5, 1 to 6. 1 to 4, 1 to 5, 1 to 6. So here we said equal sign. It just means for that supply point, which is Mount Dora, we just want to send everything out. We want to force Excel or any other softwares to, in the way that make any out move, summation of all of the outgoing moves should be equal to our capacity. So we don't want to leave anything here. We want to send everything out. So it's the reason the supplies capability was 275K. We just, with this equation, it just means we want to send everything out. It doesn't mean it should be always like this. Maybe based on your experience, you know that you have some waste. Maybe you change it to less or equal, because you might say, although your supply Mount Dora is 275,000, maybe at the end you just cancel 260,000. For such a cases, maybe we can consider less or equal. But here, based on our policy here, we just make them equal. So there is no biblical way to just define all the constraints. It just depends on the nature of your problem. In your homework or final exam, if I don't specify the policy, you are flexible in terms of policy, maybe change it to less or equal, both of them should fine. But if I mention that everything should be sent out here, you should make the equation sign to be equal. So for capacity or for the processing plants, so for example, for Ocala, we have 200K capacity. We know this, it comes from 1 to 4, from Mondora, from Ostas, which is 0.2 to the 4, also from 3 to 4. 1 to 4, 2 to 4, 3 to 4. And based on policy here, again, it just depends on how it makes sense and how you want to define the problem. I said less or equal. It just means I don't want to send more than what I can process. If I make it greater than equal to 200K, it just means Excel maybe at the end will tell you to send 210K. So you have 10 extra resource that you might waste them. So the sign of these equations, it just depends on the policy that you want to follow, or which policy is economically better. In your assignments or homework, assignments or final exam, just follow the way that makes more sense for you. here in this problem, for me, it makes sense to send everything from supply plan. Also, for the processing plan, I don't want to send more. It just makes more sense for me. So again, don't be confused with this sign of these equations, greater, equal, or less. It just depends on which policy you want to follow. In the previous problem, each policy is mentioned, like you should make at least, means you should produce more than 4,000. At max or at most 1,000, should less or equal. Your demand is fixed, so you make equal. Here we mentioned all the policies in details, but here you have some flexibility in terms of how you want to send them out and how you want to process them. Any questions? By the way, don't be scared or overwhelmed with this type of problems. And people might have bad feeling because first time you see such a problem, you even don't know how to start it, right? How to write the equation, how to write objective function. And it's okay, it's the first time you see such problems, and it's how everybody else learned them. So in prescriptive analytics, you just need to see different types of problems. So whenever people give you a new problem, you just try to see, okay, this problem might be similar to transportation problem, like here, or maybe like a manufacturing problem, like here. Okay, let's look at the solution, problem 3. Again, very similar concept, just let me follow one by one. So you have a section for decision variables. So you need to formulate your objective function in the blue one. You see, I have a formula for objective function. For each line, you need to have a formula for the left side of each line. So for each line in the left side of equations, I have a formula here. Look. If you click on them, you see the formula. Also, the right side, these numbers are here. And the last step, you should just tell Excel, where is my objective functions? Where is my decision variables? And where is my equations? The last step, as you see, the first cell is just this blue one. I'm just saying this is my objective function. You should minimize it because this is a minimization problem. This here, I'm just showing C4 to K4 for my decision variables. And for each equation, I just need to put either like here, as you see, equal sign or less or equal sign. For each equation, I have one line. So, okay, let's just make one of them. So constant color. Let me delete one of them. Okay. Now I try to make the first equation. I know the left side is in the orange cell, and left side should be less or equal right side for Ocala. So I press add, left side less or equal to 200,000 or 200K, and the sign, yeah, as you see, are less, greater, integer, binary, differences. Okay. Now I have answer. Press save, and since we want to look at the shadow price, allowable increase, decrease, binding or non-binding constraint, I'll just select all of them, press OK. Okay, look. As you see, Orlando is not a binding constraint. It doesn't participate in the final solution. And we have so many binding constraints. Let's look at the shadow price. As you see, look at Ocala and Lisberg. Their shadow price is negative. What does it mean? If I relax those equations by 1 unit, I reduce my cost. So means if you have more resources there and you have less constraint there, you are minimizing your cost even more. Looking at this problem, let me show that again. So it was Ocala and Lisberg. So let's say in future you have some investment. If you invest in Lisberg and Ocala processing plants, you're even reducing your cost more. So therefore, sensitivity analysis and these Excel reports are really important. It just makes you a better decision in future. So based on this shadow price, you understand how you can invest in future in order to make more profit for your organization. I think shadow price should be one of the more important one. Also, binding and non-binding constraint give you an idea. Look at yeah, I think these two should be enough. I mean, binding and binding constraint, shadow prices just give you more insight about basically your investment policy here. Like Orlando is not contributing, it's not binding. Maybe if you are in HR, I think 1 or 2 of you were in HR. So based on here, you're seeing that this constraint for Orlando is not contributing, it's not binding. It means you have some extra labor there. So either you lay off them or send them to Ocala or Lisberg. For example, if you're in HR, maybe you can make an offer. So you know that based on this prescriptive analytics, you are not, Orlando is not efficient, but Lisberg and Ocala needs more people. So you can offer them, just either move there or buy. I mean, you don't want layoff. Maybe you just change the department. So as you see, some prescriptive analytics somehow could be very useful for your company to, I mean, make a recruiting decision in future. So these things that you see here might be a future idea about your demand and supply. So before getting to the problem, then make a decision, you could be proactive. So you make a prescriptive analytics for future. So for sure, if you run these plans in future, you easily understand there is a shortage in Ocala and Leesburg, and you have surplus in all land in terms of human resource. So you might lose some opportunities, but if you do prescriptive analytics and your manager said, this is my capacity and this is most likely the supply. So what is your idea for recruiting people or human resources, or also maybe based on your industry, you can find other applications. Any questions? Okay, if there is no question, that's for today. I expect you have a lot of more questions, but not that much today. So, and also I have a lot of, I think some of my teachers are leaking now. So, yeah, for next class, again, we go over other types of problems. And just step by step, you expose yourself to more problems. And each problem, I recommend to look at the constraint types, look at shadow prices, and think how you can improve the situation. For example, in this problem, we understood that if you increase capacity in Ocala and Leesburg, you have less transportation costs in future, because these are the things that could happen in future. So depends on your case. I don't recommend just look at the final answer. Maybe sometimes sensitivity analysis or other reports are more important. Anyway, that's for today. If you still feel uncomfortable with the concept, please reach me later and I can go through the concept and review together and hopefully makes more sense. But again, no worries, we go over so many other types of prescriptive analytics. So these problems, I mean, each week gets easier and easier for you. Thank you very much and have a good rest of the day.
Thank you, Professor.
Thanks, Professor.
Thank you.
Thank you.
My voice didn't help that much.